Well, this is our last topic for this topic set, and it's the last topic for physics for this semester. At least I think it's even the last video. It all depends upon how far I get. I do know that in this one, when we start looking at optics, we're actually splitting optics up into two parts. We talk a little bit about mirrors, so we're looking at reflection, and we talk about lenses, and that's where we look at refraction. Okay, and so we're going to kind of do some discussion on both of those and kind of tie it back into a couple of little things when we do activities in class. So we're going to try to produce images using lenses and mirrors. One comment, since this is... Okay, so I'm back after a brief discussion with Mr. Jones. He had stopped in the room to talk to me. So anyways, as I was kind of saying, this is more than likely going to be our last video. And I do have to say that this semester of physics has been a great semester of physics. I've enjoyed actually teaching. And I'm glad that you guys have been open enough to kind of go through and bear with me as I attempt to do teaching from this new style. I think it's one of the things that keeps me kind of going as a teacher is to try new things, and this is definitely one of those things that I thought would be an interesting thing to try after teaching physics for, say, 10 years, and then all of a sudden trying to do it a different way. So I do want to thank you again for bearing with me, and I hope you've enjoyed it. I will have a survey here before you're done, so you'll be able to give me some feedback on it. And maybe in the future here, before the end of the actual school year, I may look to some of you to come in and maybe be guests on a video or something along that line if you're interested. Anyways, as I said, we are talking about optics. Whenever we start to look at optics, the very first or the simplest thing we like to look at is just a flat plane mirror, okay? And so I happen to have a flat plane mirror right here. Okay, so you can kind of see there's the camera and everything. And now a plane mirror will reflect light. And this is, again, our key thing is that to have a surface that's going to be able to reflect light, it needs to be kind of smooth. Now, basic construction of a mirror is that they take a piece of glass, and then on the back side they paint it with like kind of a metallic paint. So then what you're actually getting is you're getting a reflective surface through the glass. Now there is a slight refraction as the light rays enter in the glass, but then they hit the back of the glass here, and then they bounce up and refract, and so they come back out the same way. What really happens here is we are producing an image that we call a virtual image. Now, a virtual image is one that can't be projected, okay? So there's going to be a big difference between what's a virtual image and what's a real image, okay? And real images are images that we can project on a screen, so it's something that we can actually use as a way to like put an image on film, or to use to project an image up onto like a movie theater screen, okay? And so they're real images, okay? So there's ways that we can do that. A virtual image is nothing more than an image that appears to be inside the mirror. So now as I look inside the mirror, I see myself, and I look to be about this distance away, okay? So it's like the distance that I'm looking. Ideally, with a plane mirror, the distance that my image appears to be on the inside of the mirror is equal to the distance that I am away from the mirror, okay? So there's equal distance. Now what this really means is that images in a plane mirror are never magnified. We never see magnification. It's not like we look bigger or we look smaller. It's that we look the same distance away. Now the graphic that I pulled for this slide today is one that looks at how tall does a mirror need to be, okay, in order to see yourself in it. Now this is kind of one of those tough concepts, okay? If I want to see the top of my head all the way down to my toes, I need to have a mirror that's half my height, okay? Because I need to be able to see from my eye level into the mirror at an angle and reflect it back to see the top, and I need to be able to see down to see my feet, okay? And so again, when it comes to a plane mirror, the angles in equal the angles out, and that's the only way it works. And so half the distance, or half my height is how long the mirror needs to be, okay? okay? And so that's kind of what we're getting at with our little graphic today. So again, we're going to start talking about this real versus virtual images. We're going to talk about magnification. And now we get to the fun stuff, which is our mirrors that are kind of curved, okay? And so we like to look at curved mirrors. And I'm going to see if I've got my curved mirrors here. All right. Here we go. The first kind of curved mirror that we like to look at is this one that's called a concave mirror, okay? And a concave mirror is this. Its reflective surfaces are bent in. So in other words, we see kind of a dip. It looks like a part of a circle. Now, a lot of our concave mirrors are going to be spherical, which means that they are truly part of a circle. But the other thing that we could have with a concave mirror is something that's parabolic. Parabolic reflectors, I think, work a lot better because they have a greater ability to produce all light sources into a focal point. We usually see parabolic reflectors behind our headlights, so they're taking all the light and they're reflecting it into one intense beam. And that's usually what we like to use as a parabolic reflector. They're more expensive to make, so a spherical mirror is actually cheaper if we get it that's more of a rather than a parabolic. Now, a spherical mirror works kind of the same way. It has this kind of center of curvature. So in other words, this forms a kind of an arc, okay? And so there's going to be a center of curvature out there, and you can see in our image today we have this thing that's labeled as C, and that's my center of curvature. And then inside that center of curvature, there's going to be a focal point. In other words, all light rays as they come in are going to come in on a focal point. Now, if I kind of blow this up a little bit, okay, I'm going to draw kind of draw this in here. As a light ray comes in to a mirror that's like this, we see that there's going to be this kind of, here we go. Let's start again. As we see, I'm going to exaggerate this a little bit, but as we see a light ray come in and hit a mirror, so this is my incident ray, there's going to be kind of a normal to this, and the angle that I come in here has to be equal to the angle that I come out. And so the same thing would be true here. There'd be a normal, and the angle that I come in is going to be equal to the angle that I come out. And eventually what happens is all my rays will come to a point where they intersect, no matter where they are, because the angle in is equal to the angle out. And this point where they intersect is called my focal point. Okay, and this is exactly why we like to use these type of mirrors as reflectors on headlights, because it takes all of my light, so I put the bulb right here, all my light here would work in reverse, so all of my beams of light essentially can be directed down the road. Okay, and so that's what it works like. So I have a focal point. Now, when we do these things, we like to draw little ray diagrams. Okay, and my ray diagram is this. It's the so this arrow represents my object, and then what I do is I usually like to draw 3 rays. My first ray I do is parallel to this axis right here, okay, and I call this the principal axis. The principal axis usually goes through the center of my mirror, okay, or an apex of my mirror, and so then I draw that one, and again, because I hit the mirror, I come back angle in equals angle out, so my angle comes out and comes through my focal point. And the next ray that I like to do is I like to take a ray and I like to send it through my focal point, and anything that passes through the focal point will come back parallel to this axis. And then I have one more that actually just goes through my center of curvature, and anything that passes through the center of curvature actually bounces back because you are perpendicular to your surface at that point in time. So there's 3 rays that kind of intersect. And the point of intersection represents the point of where the light rays started from up here. And so you can see that I'm actually producing an image Okay, and this image is upside down. So this image now is inverted, and an inverted image tells me that I am producing a real image. So a real image is a image that is upside down, okay, and it could actually be caught on a screen. So now if I actually put a screen out in front of my big mirror here, and this is what we'll see in class, is that I'm able to catch that image on the screen, and so I can look at it in that sense. Now there's usually a relationship between the distance from my object to my mirror and the distance from my image to my mirror, okay? And so if I said this is my distance of my object and this is my distance of my image, this is related right back to this focal point, okay? So 1 over the focal length is equal to 1 over the distance of the object plus 1 over the distance of the image. Okay, and so that's a relationship, a mathematical relationship that ties those two things together. There's also a mathematical relationship that looks at the magnification of an object, and so when we look at this, it's the distance of the image divided by the distance of the object, or we could say the height of the image divided by the height of the object. Okay, so if I know the object's height and I know the image height, I know what kind of magnification I produce. The same would be true is that I know maybe the magnification, what my lens is going to be able to produce, and so then I can estimate how big my object's going to be. Now, as we start to move an object, so if we move our object in a little bit closer here, okay, what happens again is that our rays, so again, if I looked at it here, here's my object, okay, there. My first ray comes in, parallel, comes down through the focal point, okay. My second one goes through the focal point, comes back, parallel, and then my third one is through the center of curvature, okay. And so I'm getting a point over here where my image is starting to appear, okay, and my image starts to slide back. And so what happens is I get closer to that center of curvature and I start to match my sizes. Now again, as I start to get closer and closer to my focal point, my image gets a little further back. At some point in time, I can get my image inside my focal length, okay, and this is kind of the one thing that happens is anytime I'm looking into one of these mirrors, okay, I see myself, okay, upside down. I see everything upside down. The moment I get inside of my focal length, all of a sudden, I see myself right side up, okay, and so I know that I'm producing now a virtual image. So a virtual image is produced anytime we bring our object inside that focal length. And we get then a magnification that's going to be a lot bigger. So when we draw this one, we again take a line that would pass through our focal length, okay, comes back parallel. You see that line doesn't cross. And we take one that would go parallel and would have to come back through my focal length. And these two rays don't cross. They don't cross, which means that I'm showing something that's going to be a non-real image. But if I extend these things back, okay, I'm actually producing then an object that would be bigger, it would be upright, and it's on this side of the mirror, okay, and so that's how I produce that. Now I see that I'm kind of running short on my time here, and so I'd like to maybe stop here and then switch over to the other type of mirror, and then we'll talk lenses as well. And so the video will be not only this one, but it'll be the other one as well, and we'll talk optics in class then tomorrow.